Hello, my name is Cristali Ruiz Roena, and I'm a PhD student at the University of Texas at El Paso, and today I'm going to be presenting an implementation for a correctly rounded logarithm. This presentation was revised by my student Mayra Robles. I would like to preface this presentation by saying that our intent is to show the audience how we can implement a correctly rounded function, in this case, the logarithm. However, we might touch into some considerations that we should have whenever we're doing this kind of implementations, so the audience can see and consider whenever they are doing this themselves. The first thing we want to ask ourselves is, why does it matter? Why do we want correctly rounded function? And to do that, the first thing we got to do is define what it is. A correctly rounded function is defined as a function that is going to return the closest representable value to an exact mathematical result. And what does that mean? I have a very simple example here. Let's say that we have a set of representable number of 1, 2, 3. I have a function f and a value x over which I want to evaluate the function. When I do that, the exact value is 1.2. But within my set of representable values, I don't have 1.2. So in that case, the function should return 1, which is the closest representable value. And as you can see, this is going to ensure consistency across implementation. So that means that I can move whatever I'm doing to another system or another implementation, and I'll still have the same result. Since we're going to be working with floating point throughout the whole presentation, we do need to adhere to the IEEE 754 standard. And when it regards to correctly rounded functions, there's no specific requirement, but that the result should be consistent with the rounding that it's used. Things that we should take into consideration whenever we are implementing these functions, and we can say that it's almost a general rule to most of the functions that we want to implement in computers, is that first, that we need speed. We want to have fast computations without compromising our result or the performance of the function per se. The accuracy whenever we are deriving our values. Resource efficiency, that we are using whatever we have to its most capacity. And mathematical properties, rounding direction and range limits, are more in the size of just making sure that the implementation that we have is stable. So why is it important? The first thing is because it facilitates proof. In that case, that means that we do have a specific number to look for whenever we are evaluating a function. So that means that we can prove if it's correct or not. And I want you to think especially about irrational numbers when it comes to correctly rounded, because I think this is a very good example of why will we want that. And in this case, I am kind of bringing the number pi, which I think whenever we think of it, I see 3.14. And of course, I know that there's some numbers after that, but I think the general rule is that whenever we're going to do rough calculations, we don't have the number pi in all calculators, we're going to have, we're just going to use 3.14. And well, this is an interesting situation because we have an approximation that's basically been rounded for us to use. And the problem with irrational numbers is that they are infinitely precise. So that means that we don't know the exact number because it's kind of infinite in a sense. And since we're working with a floating point, we do know that the standard has a fixed amount of bits that it can use, but also we know that we don't have infinite storage, so it will be impossible for us to save the exact number in this case. So it comes to a very important part, which is rounding. Rounding, it's the function that it's helping us know what's the closest representable value in this case. And why not 3.15? Why 3.14? To talk a little bit about the standard, I have here the format kind of, and it's a very overview of what the standard is. If you want to go into more details, you can probably download it and read it. However, I just want to kind of point out some details here and there. It's basically rules what's floating point, its format. It defines some other format, single, double, etc. And the idea of having consistency whenever we're implementing that format, it's because across computers, it's widely used, so we want to be compatible with everything that we have. So how is it different to an actual implementation? The standard are just rules, kind of. An implementation is actually a piece of code, an algorithm that it's implementing whatever the standards it's saying. So in this case, we are actually going to present how to implement a correctly rounded function for every input or every x in this case. What's the role of rounding? So rounding is the function that it's mapping my whatever value I have to my closest representation. So according to the standards, we have 4 rounding modes. It's round down, round up, round to even, and round to nearest, which ties to even. I would say that the round to nearest is the classic, what we are kind of taught whenever we're in school. And I do want to say that closestness is relative to the rounding mode. Let's say that I'm using round down. It means that my pi example will be 2.14. But if I'm rounding up, that means that the closest value will be 3.15. So it's important to take into consideration that closeness, it's closely related to the rounding mode that I'm using. And I have to assure that it's consistent whenever I use the same rounding mode. So now we have all the ingredients. Now we go to implement our function. I want you to consider for a second that we have the elementary functions, and then we have the basic arithmetic functions and transcendental functions underneath. And when we think about the basic arithmetic functions, and I tell you addition, subtraction, multiplication, and division, you can probably come up with a finite step algorithm that it's going to give you a very good result. And it's pretty straightforward. However, if we talk about transcendental functions, sin, exponential, log, let's for example say the logarithm of 3.5, it's not a straightforward process. It's not an algorithm that is just as simple. So in that case, we need to come up with an approximation of what that value is. Of course, we won't know for sure what it is, because in transcendental functions we can only evaluate exactly or know for sure the values in critical points. So the rest might be a little bit trickier to get. However, the idea is that if we have a smooth function, then we can use a polynomial or an infinite polynomial in this case to approximate it. And of course, since we can't have infinity, we have to truncate the evaluation to a certain amount of precision that we might have available. So the problem here becomes, well, for correct rounding, I need an exact value, right? I need to make sure that the exact value is rounded correctly. But if I can't have an exact value, well, that means that my approximation has to round to the same place that my exact value should round to. without knowing the exact value. So that's kind of the problem with the transcendental functions. And it's a pretty interesting thing to consider. And it brings up a tiny dilemma that it's called the table maker's dilemma. And just to give a bit of background, if we go back to before we had computers and calculators, if we needed to know what's the logarithm of 3.5, we need to look into these tables which were going to give us like an approximate of what the value was. So in this case, we for sure have people making those tables, and the table's dilemma is that whenever I have a value that falls kind of between two intervals or within two possible ranges, where do I round it to? It's in the limit, so where does it round up? Does it round down? How do I do that? And let's say that fast forward, we still have the same problem. I would just say that it's kind of a finer granularity problem in the sense that it's not so up in the list of problems, but kind of in the lower side of our precision. So let's say that there's this value that we don't know for the evaluation of the function, which is y, and that's the exact value. And then we have y hat, which is our estimation. We don't know what the exact value is. However, we do know that that value is within an error of epsilon 1. And I do know that error. So that means that I can construct an interval around my estimation to kind of map where in all my range the exact value may lie. So once I have that, I can basically just round my limits, and if they all round to the same place, well, that means that my exact representation is also going to round to the same place, right? Because it's known to be contained within those bounds. However, what happens if my interval includes a midpoint? It includes a representation that it's in between. So that's the hardest part to do. That's actually the table maker's dilemma, because I don't know the exact value. I do know my interval bounds. I do know my estimate, but I can't assure that my exact value is going to be rounded to the same side, because one of my interval bounds, it's rounding to another place. So in that case, how can I ensure that I can do a correct rounding in that case? So the way we solve this problem is just we make the interval smaller in a way that it doesn't cross any midpoint. And to do that, we have to determine what that epsilon is going to be beforehand. And in this case, we need to find the smallest distance that there can possibly be between an exact value and a midpoint. So that's the smallest, because then that means that I have to make my error smaller than that. So I make sure that I never cross any midpoints. And in this case, doing that is computationally expensive and very extensive, in the sense that we need to look for the hard to round cases, which is what we call them. And once we have them, we take the worst of the hard to round cases, and then we use that as kind of the pivot for the rest of my calculations. So in that case, that tiny distance becomes the distance that I need to have for all the others values. So in this case, for the logarithm, we do know what the worst case is, and it's this one right here. And it establishes that we need for double-double at least 115 significant digits to do a correctly rounded result. And now I kind of know how to avoid the pitfall of not being consistent whenever I'm rounding. But now, how do I evaluate if I'm within the bounds or not? Because there should be a test that it's simple enough. It's simple in the sense that it doesn't require many arithmetic operations. Simple as possible, that can tell me if my result at a certain point is correctly rounded. In this case, we have the SIP test, which ensured that we have a small enough interval to attain correctly rounded results. And the idea is that it would check if my interval falls exactly within one side or the other of the of the rounding. Basically, and ideally, this test is repeated until the conditions are basically satisfied, because otherwise we can't say that we have correctly rounded results. So in this case, this is basically a guarantee that they are correctly rounded. One thing that whenever we have the test and let's say that it all falls within an interval, that's cool. Then we're good. However, what happens if it doesn't? In this case, we introduce the concept of what's a fast pass and then a slow path. And the idea is that whenever we get a value, we go through the fast path and we do things as best as we can, and we follow what you will see in a bit. But if at the end over that implementation, I don't have a correctly rounded result, that means that I have to go through a slow path to actually get there. And you might say, well, that seems like it's not worth it, because why not do always the slow path, I'm sorry. So in this case, probabilistically, it's very unlikely that we might need to use the slow path. I'm not saying impossible. I would say that compared to the many times that the fast pace will be enough, slow path, it's not used as much. And in that case, we rely on those statistics to say that most of the time we will use the fast path without actually having to go into a more extensive implementation to get our result. And now we go into how do we approximate a polynomial. Ideally, the polynomial uses a standard. Evaluating a polynomial uses basic arithmetic operations, and that makes it a very suitable option whenever we are doing on approximations. And in this case, I bring the Taylor series as an example, where we have ideally infinite terms. However, since we are not in an infinite world, we need to, in an infinite computational world, then we need to truncate that series. And just to illustrate what adding degrees, what kind of adding further calculations to these polynomials do, you can note here that the line in blue that has 1 degree is 1 order, it's just a line. However, let's compare it to the cyan degree 10 expansion that we have. You will see that it closely resembles the function. So you can probably, if we take black to be the actual logarithm, and then we see the cyan path, that it's very closely to the function. Of all of them, I would say it's the closest one. So as we add more degrees, we make an approximation way better for the function. But problem is, how many terms do we need to make an approximation accurate? And it's feasible, but it's definitely expensive. And let's say that I'm taking a value, an x that is very, very large. In this case, how do I handle it? Because I mean, as I would say that as x is bigger, I will need more degrees to actually be more accurate. And in this case, how can we reduce the amount of computations? What can we do to make it better? Of course, one thing to note here, for the sake of this presentation, we're not going to use a Taylor polynomial. Instead, we're using polynomial approximation in Solia, which is FP minimax, and it's a method that is described in this paper here by Brisebarre and Chevillard. I would say the key thing about this method is that it provides coefficients for the polynomial that have exact representations in a specific format. In this case, floating point. If we use double, or whatever we're using, you will see in a bit how that is specified in Solia. So I already kind of make the case that we don't exactly want to have as many degrees, especially if we have bigger x's. So in this case, we use a range reduction technique, which the idea is that I'm going to take my input and I'm going to reduce it so I can have a smaller range of what I can evaluate. And the idea is that I will take the input and I will decompose it in a way that some of the values I can pre-computate, and also I will have the benefit of just evaluating my function over a smaller range. So it kind of makes it a better way to implement it and still get fairly good results. I do want to add that range reduction is not a method. It's not saying that it's an A algorithm, but it's a general technique. Whenever you are doing a range reduction for any of the functions, you have to take into consideration the properties of the function, what function you're using, what's the range, and things like that. So it's not just something you can take from here and then apply it somewhere else exactly. You have to take other things into consideration. And I also want to add that this is not the only implementation that exists for logarithm. If it's correctly rounded, they all should return the same result, but there's not one, but there can be many. So we have gone over some of the pitfalls, some of the things that we should consider. We know what a correctly rounded function is. We have the rounding mode that we are going to use. We are going to use polynomials to get our approximation, and then we also have a test to determine if our function, if our result is correctly rounded. So it seems like we have all the ingredients, so now we cook. First thing we're going to do is that the input x that we receive, we're going to decompose it into something that reassembles the floating point format. And why is that? We're working in floating points, so that means that my input is also going to have that format. Once I have that, you can see 2 over f times thou, and thou is between 1 and 2. I have already reduced significantly the range in which I have to evaluate x, in this case thou now. So once I take that out, you will see that I have f times logarithm of 2, and logarithm of 2 is a constant. That means that I can probably do a pre-calculation for that value and have it in hand whenever I have to do that multiplication. So you can see that it definitely helps to do this just tiny decomposing of using the floating point. So the problem right now is that our reduction so far, it's prompt to catastrophic cancellation. That means that the very small precise values can be lost, and that means that there's a loss in accuracy in a sense. So in order to make my input kind of safer, we converted to an interval of square root of 2 over 2 and square root of 2. And eventually I want my DAO to be converted to that m, right? To that, I'm aiming to be in that interval. So what we observe here is that it's just basically multiplying square root of 2 over 2 in both sides of the boundary, and that's exactly what I do next. I take my DAO and then I make a new DAO that it's scaled by that number. And once I have that, my intervals kind of change a little bit. Now I'm my new DAO is between square root of 2 and 2 times the square root of 2. But I still have to divide by 2 to be in the same range as m. So instead, what I do next is that I try to find if within DAO there fits a 2. If it does, then it means that I can take 2 out. Otherwise, well, it's 0. So that means that G can only be 2 things, and it's kind of bounded by the limits. You will see that basically my max limit here can only have a 2, and the square root of 2 doesn't even have a whole 2. So it's fair to say that G is only going to be 0 and 1. And that's kind of our way of just dividing by 2 without actually doing so for the DAO new that we have. After I have that, I transform my new number into, again, something that resembles the floating point format, but with the new DAO and the G that I just calculated. So we have 2 over negative G times my new DAO. And of course, since I'm kind of going down in the stack and just transforming my value, eventually I have to cancel whatever changes I made to the result, for the result. So in that case, I need to add back what I took out with G, and my new exponent is going to be F plus G. And I save that because that's the exponent that's later going to be used for further down the road after I have evaluated my polynomial. And now I'm kind of in a safer range, and I can avoid most times catastrophic cancellation. Now, we have seen that if we deconstruct our input in a very specific manner, we might be able to get some constants out that we can calculate beforehand. And right now we're going to do something similar, in which we're going to invent this number C. And if you can observe in the argument, it's a multiplication of 1. So it's not going to exactly affect our math here, but it's going to help us reduce the argument further. So once we do that tiny transformation here, we take out a logarithm of C. And for now, don't worry about what C is going to be, just bear with me. Just know that T of C is going to be a table that it's going to contain the values of negative logarithm of C. And after that, another thing that is desirable is that I want to evaluate my logarithm within 1 plus R representations. So that means that the only thing that I have to do is what I have left, which is C times M, and say C times M is equal to 1 plus R, and then that's going to give me what R should be in order for me to use logarithm of 1 plus R. And once I have that, you can see that we have transformed again our input into, well, in this case m, I have transformed it into t of c, which I'm going to look up in a table, and then the logarithm of 1 plus r, which still need to be evaluated using a polynomial. So now what's c? C, I'm going to define it as 1 over m, which is the m that I reduced in the previous step, and then multiply it by 1 plus epsilon. And one thing to notice is that my r, it's basically that epsilon there, and it should be around a value of 2 over negative 7. That is equal, or it's equal or less to that value. And so far we have determined what m is, what t is going to be. We're using a table to determine that, but we actually need the c's. But I'm defining c as a function of m. So that means that I need m to determine c, so I can then determine t. And in this case, what we're going to do is that we are also going to map c to a table. So in this case, we can get the pre-calculated values to c as well. And in that case, since I need c, how can I look up for c? And that's where I will need an index, a function that will tell me what's the value of c that I need, so I can then return it to t, so t can know what's the value in specific place is going to be for c. And just a very simple step here. We're not going to look exactly on what these values are. Just know that these are for alignment in a way with the table, because you can see, for example, that square root of 2 over 2, it's basically our lower limit. So it's just aligning our range of m's with the indexes that we're going to have in the table. In this case, w is going to be a constant. Of course, if I change w, the whole implementation is going to change. Take into consideration that w, it's defining how big our table is going to be. So of course, it's going to affect our values, because if we choose a bigger w, that means that we're going to have bigger values and much more values on our table, which in terms is going to affect the rest of our calculations. So the next thing that we do is that we take m, we subtract m min, which seems logical because we kind of want to align it to what's the minimum that we have. And then we do a fuse multiply addition, where we multiply that mu times s1 plus s2. And once we have that, we use this formula here to determine what's the specific I that I need. One thing to point out here is that t is eventually going to become a function of I as well, because if I'm going to pre-calculate c, then that means that once I have all the c's, I can probably just use my I to calculate what my t is going to be. Because if I'm dependent on c, and c is always going to be the same, then that means that I can also say t directly and retrieve it just using I. And once we have that, we have make all this transformation and everything, what we have left is something that looks like this. The logarithm of m, which I had in my first reduction, is going to be equals to table t, whatever is in table t in the index I, plus the logarithm of 1 plus r, where r is equal to the c that I have times m minus 1. And since r, which is our reduced argument, it's ready, then that means that I now can evaluate my polynomial for that specific r. Of course, I have reduced the argument as much as I can at this point, so it's fair to say that it's ready to do the approximation. Now, how do we evaluate the polynomial? In this case, we're going to use the Horner's method, which is a nested method, unlike the naive, standard, or I would say classic way of looking at a polynomial. The idea of these, if you look at it carefully, is that we have factored out the x. So basically, we can evaluate the polynomial starting with the highest coefficient up, or well, you'll say up if you consider that up it's lower, but it's kind of just going down. So it means that you start with the highest coefficient and then you go into the second to last, and so on and so on. And this just makes it easier to handle the whole thing. And you will see that it's a lot of fuse, multiply, and additions. That it's an instruction that we are kind of taking advantage of in this case. As we saw in the range reduction, now we have some constant that we can pre-calculate. We have logarithm of 2. We also have the tables for C and the table for T. And now we're going to use Solia so we can kind of fill out those constants beforehand and then go into our implementation. To give a brief introduction, Solia is both an environment and a library where you can do floating point development, basically. And it has two cool features. The first one is it's a certified supreme norm. And to explain what a certified supreme norm is, think about my approximation and think about the actual function. The certified supreme norm means that I can construct a very tight interval between my polynomial approximation and the actual function. And I can tell for sure that my error is within that interval. So that means that it's very, very, very good whenever we want to satisfy certain constraints. So, and that leads to the second feature, which is that it can satisfy error bounds because it's certified to know a maximum error within a tight interval. So it, by just comparing, you can basically get to very, very good approximation and close approximations in this case. And of course, it will produce exactly representable coefficients for a given format, especially depending on the functions that we are using. In this case, FB min max, which we will see in a bit. And using Solia to define this mathematical constant with high precision, it's highly used in the arithmetic world, and it has a C-like structure, so it's not like you have to learn a new language. It does have some differences, but you'll see that it's very C-like. So now we go into actual code. The first thing that we see is that we have to define what's the number of bits that we're going to use floating point wise. So in this case it's 64. Then we have 53 for the significant or mantissa, and then we have some values that we're going to use to determine the errors. And also W, which as I mentioned before, it's going to kind of control, it's a constant that's kind of controlling the length of our tables. After that, I add some other values, including kind of the rest of the bits that are used for the floating point format and K prime. Then to look carefully on these values, we see B, which is the square root of 2, that it's a the value that we're going to use to multiply our thou with to make a new thou, as if you recall. Then we also have S1 and S2, which are the values that are going to help us align our indices in a table with the M that we are provided. Then we do something that it's pretty typical, and I'm just introducing it, which is called compensating arithmetics. And the idea is that although you won't see arithmetic here, but the representation of the numbers changes a little bit, where I will have a main term in this case called high, and then I have two compensation terms, which are the first being mean and the second being low. So it kind of follows that high, mid, low pattern, but that's basically a main term and two compensation terms. And you'll see that down to not all the values, but many of them that are important in our whole process. So then we do the epsilon log of 2, in which we're just trying to determine what's the error of the value that we just calculated. And of course, remember that Solia is going to help us satisfy some error bounds. So you will see throughout the whole process that whenever we kind of produce a value, we are going to test that value is within the bounds that are acceptable for our constants. And that's important because, of course, whenever we are doing these operations, we're introducing errors. So we want to minimize that, and to kind of satisfy those constraints, we need to have and be sure of what those are, so the program can evaluate them. Then we have the min and max, as you can see here, just the straight values that we're going to have. And then once we calculate those, we determine what's the I max and then the I min for the tables. And that's important because we want to know how many terms we will need for the table. And as you can see here, there are other variables that we're going to use later on the indexes to determine what's the indexes that we need to access in the tables. And once we have all those variables ready, then we prepare that for the loop. We prepare to fill out tables. So you see that we have the C table, and with the T table we do the compensation arithmetics kind of style here, where I divide the number into 3 parts for later calculations. So once I have everything ready, I go into the actual loop that it's going to help me fill up the tables. And I have kappa underbar and kappa overbar, and as the numbers probably is telling you, underbar and overbar, the idea is that I'm establishing the bounds for each of the indexes on the tables. Once I have that, I use, of course, an m underbar and an overbar to determine what are the limits for m. Once I have that, I kind of go into kind of mapping that to a specific I. Of course, once I have done all that, the next thing is going to be to introduce the table that I calculated or evaluated for C. And once I have that, I can use C to determine what's R overbar and R underbar. Remember that when we reduce the argument, then we make R dependent on C. So that's why this step is important. Because now what we're trying to do is that whenever we produce a new C, we want to keep track of what our R min and R max are going to be. And that's going to be important because you'll see later. And then, since I already have C, it just logically that I would just then go and pre-compute C. And this is the part where I told you that since I already know what C is going to be for a specific I, then I can just use the index to access C as well. And in here, you would just see that I do some compensating arithmetics in the values. I test that it is within the bounds that I desire for this constant. And after that, I, of course, more testing. And after that, I saved the values to the tables. So once I have that, remember that we were testing the R's for min and max, and we were keeping track of that. So once I have that, I have the domain of my R. So I know within which values my R are going to be. And now I establish a target to satisfy the error bound later. So this is the target that I'm setting for that specific error. And finally, I define what's the function that I want to eventually evaluate on my polynomial. What I do next is that I use a guess degree to determine the amount of degrees that I will need to satisfy the constraint that I just defined. And once I have that, then I go into the actual polynomial approximation. And in this case, not evaluating the polynomial, but getting the coefficients. And as you can see here, I give the FP min and max, the functions we have been talking about. I give it the function that I want to approximate, the amount of degrees, the format that I want the coefficients to be in, and then I give it the domain of my reduced argument. Once I have that, I use the function, of course it returns my coefficients and everything, but once I have that, I do the suprema norm function, which in this case, if you recall, is one of the features of Solia, where I can determine what's the maximum error between the polynomial that I just produced and the real function. And you basically ask if it can be satisfied up to a certain epsilon, which you have here. So now we have our values, and using some helper functions, we just export them and then introduce them to our C implementation, and that leads us to the actual implementation of our function. So I'm going to assume that all the variables that I'm going to use here are already declared, but just bear with me because it's just easier and we will skip just a lot of tedious work. So now I receive X in a binary 64 type. The first thing that I do is I convert it to bits so that I can evaluate and manipulate it easier. And of course I keep track of the exponent offset, because if I have some normal numbers or anything that I need to change, then I need to keep track of that. After that, I go for special cases. I check if this is normal, if we need to make any changes to the exponent offset. And also I want to look into the very specific points in the graph that I may not have a value for. So for example, 0, negative numbers, which you will see here. In that case, I will need to raise division by 0 exception, which is actually specified by the standard. Once I have made sure that I don't have anything to handle or anything that I should take care of to raise, then I go straight into doing my argument transformation with the argument reduction that I already defined. So the first thing that we do is that once we have the bits, we separate them into F and thou. Then I take the thou, I multiply by the square root of 2, which is the b that I defined in Solia, and I have a new thou. After that, I need to divide by 2, as you recall. And that's what I'm going to do next with that thou new and get what's g. Of course, I have to scale the thou that I have originally with that g, and then account for that g in the exponent that I'm going to use later, plus the f that I have originally. If you recall, just when we take a g out, we also have to account it back into the exponent so we can have kind of a correct result in that sense for the exponent. Once I have what my exponent is going to be, I just put it into place for a future reference and just let it there. Next thing I'm going to do is that when using my new m, I need to determine what's the index that I need to access my tables. And that's basically what I'm going to do Next, once I have it, I get my result for C and also get my results for T. And remember the compensation arithmetics that I was talking about? We kind of do that very often actually in this code, where you will see that we are multiplying a specific number and we are splitting it into high and low. Once I have that, of course, with C, I can determine what's my R. Because, again, if you recall, I already have M. C is dependent on M. And then C, M, and 1, it's what I need to kind of calculate what R is going to be. And once I have my R, I can then start evaluating my polynomial. And I start, of course, using the Horner method with the highest degree coefficient, which in this case is going to be 9, and you go down. And as you keep adding, and multiplying the coefficients, you will see that there will come a time where we are going to kind of slow down and do compensation arithmetics, because in the lower coefficients we want it to be more precise in that sense, more accurate. So once we have evaluated our polynomial and we have a good approximation of what our logarithm of 1 plus r it's going to be, we still have to kind of undo whatever we did on our range reduction, which, if you recall, one of the first things that we did is multiply our exponent times the logarithm of 2. So that's the very first thing that we did when we reduced the argument. And after that, that's where we're using our exponent. After I'm done with that, I need to then add everything, and after that I kind of have an approximation value already. Then what I'm going to do is that I need to test if my evaluation right now it's enough. That's where we use the sieve test that I presented very early in the presentation. And if it passes, perfect. I have a correctly rounded value. I can just return that. However, if I don't, then I have to go into an accurate phase, which we also talk about it as a slow path, where I need to compute maybe more precisely a value for my approximation that will round correctly. And after I'm done with that phase, then I can also I can actually return my correctly rounded value. So now we're done with our implementation. We can say that we have a correctly rounded logarithmic function. And in this case, what we do next is what I would say any engineer will do, which is just testing, and then the scientific part is proving. And in testing, ideally we want to use values that already exist and we know the results for, and we will compare that, especially some of the hard to round cases, which will help us kind of validate that our function is actually working properly and as we expect. And of course, we also, in the proof bar, we use GAPA proof, which it's a tool that it's going to help us formally verify the computed values given an error bound. So in a sense, it ensures that, makes sure that our calculations stay within an error bound of that is previously defined. Of course, this material it's all in a repository that I just linked in my references, so feel free to look at it and see what we have there. There's the GAPA proof and also some testing and the script and the whole thing that I presented as the implementation side of it. Thank you so much for your attention, and just in case, I'm going to add these references to the description, so you can definitely look over if you are interested. Thank you so much.